Hi and welcome to video notes 8.7 on exponential graphing. You can consider this part 2 or day 2, but it's on exponential graphing specifically. So let's get right into it. The first thing we should note with this exponential graphing is kind of what its general shape was. And don't forget, we kind of said that it's ever increasing between the y values that eventually takes off and has a steep curve to it. And again, we could have a decay, which we said was possible as well, meaning that would have a steep curve, but it would be in a decreasing fashion from left to right, right? So we always look at them from left to right. This is a growth and this was a decay. So considering that, there's a new piece that we haven't ever talked about before, at least in our class, which is an asymptote. Because these values, as they decrease, are a percentage, they never get to pass a certain boundary or certain point. And in our base form, okay, so in the standard form where we're talking about a being our initial value, b being our growth factor, and then x, our input, being the exponent, in that general form, our asymptotes always in the same location. So without any changes, without any translations, we find that our asymptote was where y equals 0, or along the x-axis is another way to look at that. All right, so now that we have that, it never crosses this line. So it doesn't matter how I draw this curve or how it takes place. And right now I'm going to make an exponential function where the b value is greater than, that should be 1 right there. Let me go ahead and change that. Where the b value is greater than 1. We'll explore that in just a second, meaning that it's a growth, meaning that it's going to start really close to this line and it's going to get a little bit bigger and a little bit bigger and a little bit bigger. And eventually you're going to start to see that change because it adds upon itself, right? The increase becomes greater and greater as we go along. So it's going to take this steep curve and it's going to increase upward. Okay, so there's that general shape. It will never cross that asymptote. It will get infinitely, but never cross that asymptote. So it's always a good place to start when you're graphing, is to go ahead and mark that asymptote down, and then you know where the boundary is. Again, in this particular form here. So now that we've got that down with an asymptote, let's talk about some general points that are always a good place to start, especially if you're sketching, right? And the difference between sketching and graphing for an exponential is, with graphing, we're just going to build a table. It's not like linears where we can kind of predict where it goes. It's kind of I don't want to say unpredictable, but not accurate in our predictions. So if we're graphing, we're making a table of values. We'll see that in a second. But if we're sketching, we can use a couple points here that are fairly common, close to 0, because these can get really big or really small really fast. So these are the points I'd like you to use. The first point I want to talk about, if you've noticed, has an x-coordinate of 0, which makes this the y-intercept, right, or the initial value of this particular function. That will always cross the x-axis. It'll be somewhere in that vicinity, again, in this basic form, but as we change it, it'll move around. So that's a nice point to plot because you're putting in 0 for an exponent, and that's usually a good value to work with. Additionally, there's another point on here that would be good to work with, which is 1 and whatever its output is. In this case, it's going to be 1 and AB. Again, it's pretty easy to take the A value and multiply it by the B value. That's not a hard calculation, so you can usually get that point really quickly. And to finish it off, we'll do the next point, which would be 2 and, oops, I didn't write that the right way, 2 and A times B squared. Again, something that you can do. The reason that I bring these three points up is because this can get really big really fast, and you can see that we can shoot right off of our graph pretty quickly. And then on the left side, you'll see that it gets infinitely close, so all these points become hard to determine between them. So these 3 points really kind of set a nice sketch for this shape. You know that in some fashion you're going to be increasing or decreasing out of these points, and they're going to get infinitely close to the asymptote. So these are great for sketching, okay? Let's talk quickly about domain and range, and then we'll talk about the difference between growth and decay. So the domain then, don't forget, is how far this function exists to the left and right. Meaning if I look at these individual integers here, or decimals, where will it go? How far could I go out and still look up and see that function? Well, if you could guess, you're going to say, hey, this is going all the way out to negative infinity. Right? So if we're going to use our inequality notation, we'd say it goes out to negative infinity, not including x to represent domain. And then we got to look at the right. Now you're like, Mr. Allen, that's going straight up. So is there another asymptote right here? Absolutely not. There is not an asymptote. As much as that looks like, let me draw that back in. Much as it looks like it's going almost completely vertical, it's still ever so slightly increasing outward. So it's going mostly upward, but it's still going to the right a little bit, which means that it will eventually reach infinity. So if we close off our domain there, that's one way to write it. And we know another way to represent this, right? We could say the words all real numbers, or we could put a bold R. In that case, most of the domains for this are going to be all real numbers. All right, but let's take a look at the range where that changes just a bit. The range is the same concept, but it is if I travel along the y-axis and I look out in either direction, where would I see this function? How far up could I go to find it? And or how far down could I go and look over and see it? Well, you'll notice if you look from the left or right of any of these negative numbers, here in this particular example, we don't see it because it's below that asymptote. So for our range, it will be limited to the lowest bound of whatever the asymptote happens to be. So I'm going to scoot down a little bit here. So our range in this particular scenario is where we said y was equal to 0. So it's going to be 0, which we can be not on. We can't touch it and never cross it, so it can't be included underneath. And we'll put our y to represent range. And then, of course, it's going to go up. We can see how upwards it goes. Here, let me scroll down. I'm getting stuck on my scrolling. All right, so if I scroll down, look, it's going up forever. It's going to reach positive infinity pretty easily. So let's go back here and put our upper bound as positive infinity. So that's going to be the best way to write the range there. So now let's talk about the difference between a growth and a decay as a type of function. We've referenced it, hinted at it a few times. Again, referencing our base form of it. So a, our initial value, times our growth factor, raised to our exponent, our input number of changes over time, right? If that's the scenario, we have that base form. If this b value right in the center, and that's really what we're going to focus on, this b value right in the center, if it's greater than 1, meaning that it's a whole number as 1 or larger, it doesn't have to be a whole number, it can be any decimal greater than 1, it could be 1.00001, that's a growth. Really small growth, but a growth. And the larger that gets, the steeper this curve happens to be. So in this scenario, this curve here is growth. And what we want to say then is that it gets farther from 0 as we move from left to right. Okay, so as I go along, notice here's 0 for the y-axis, or your asymptote's another way to go look for it. It gets farther from your asymptote as you increase from left to right. Notice I'm getting farther and farther and farther. Well, there's another scenario for this under the growth. If we make a negative, it flips our graph. We're pretty comfortable with that concept. So what does a flipped graph look like in this scenario then? So I would be traveling along that asymptote, right? Because we're flipped, it's going to flip down, it's going to go downwards, and I'm going to increasingly get away from this asymptote as I go along. And you're like, well, isn't that a decay because it's going into the negative numbers? Well, no. What you have to pay attention to is it getting farther from 0, or we're going to say that our asymptote in this case, is it getting farther from that value? And it is. It's just doing it in a negative direction. So what we like to say this is, and as awkward as it may sound to you, you got to get comfortable with it, is that this is a negative growth. Left to right, it's getting farther from our asymptote, farther from 0, either up or down, those are both growths. So then, as you figure, a decay then is an exponential function that gets closer to the asymptote or closer to the 0 as you go from left to right. Again, everything's in reference to that. Let me mark my asymptote in here. I'll mark it over here. I forgot to mark it. And so that can also, this would be a positive, this would be a positive decay. It's decaying from the positive side of the values down closer to the asymptote, close to but never crossing. A negative decay would get closer on the negative side of the values and get close to that asymptote but never cross. In that fashion, that's a negative decay. So I know it's awkward to say a negative decay. You're like, wait, decay means down. But this is a downward motion, right, towards the asymptote from the negative side. So make sure that you know those, put some time into it, but let's take a look and see if we can identify these. All right, so you can say it as I go or pause the videos, mark them all, and then do it with me. But looking at these, so I'm going to look at this function here. Are we getting closer or farther from our asymptote? And in this case, we can tell we're getting closer. And it's from the positive side of things, so we're going to say positive decay. All right, looking at this one, we notice we're getting farther from, here's our asymptote, getting farther from our asymptote as we move along, right? So it's increasing. So if it's increasing, but we're increasing in the negative fashion, this is going to be a negative growth, okay? Looking at this one here, our asymptote has moved, it's shifted down a little bit. That would be where our asymptote would take place. So again, we're getting farther from that asymptote as we progress. So that's an increasing function, and we're increasing towards the positive, so this would be a positive growth. Starting in the negative fashion, but it's going to end as a positive growth. All right, and then this last one here, we can see that our asymptote has again been moved. It looks like it's been shifted up, and we're getting closer to that asymptote, so that means that it's a decay, and we're doing that from the negative side. So this is going to be a negative decay. I just want to highlight, again, the difference between decay and growth is one, if it's a decay, that growth factor, B, is going to be a decimal. Notice we said between 0 and 1. If it's larger than 1, it's a growth. That's how you tell the difference. All right, so growing down here, we're going to actually talk about one quick sketching and then one quick graphing. Okay, you'll notice that first that our b values is something to look at, right? Both of our b values here on our examples are greater than 1. So these are both growths, just to kind of point that out. Okay, so this would be what it would look like if we were graphing. Notice I just took this function, right? And don't forget, you can see I highlighted that the a value is -1 there. And I plugged in different values of x, and I got out different values of y, and I plotted those points and drew that graph, making sure to mark my asymptote. Okay, notice the form, a, b to the x, and that's the form that this works with. All right, but if I was going to sketch and use those points that we talked about, I would use this one here. I'm going to do it on this example. So looking at the first point, which would be our y-intercept, which would be 0, and then whatever our a value is. Well, our a value is right here, right? That's our a value. So it's 0 and 1/2. See how quick that is? There's no calculation. And if I put 1 down, right, here's 1a times b. Well, here's your a, here's your b. 1/2 times 2 is just 1. And then again, let's plug in 2, because that would be the last sketching point we'd use, and it's going to be a times b squared. Well, here's b, square it, that makes 4 times 1/2, or 2. So there's our points that we're going to go ahead and graph. So we're going to go to 0 and 1/2. So 0 and 1/2, there's our first point, and we're going to go to 1, 1, and we're going to go to 2, 2. While that's kind of hard to disseminate, you have to understand what the general shape of an exponential is. You have to know that this is a growth, so it should be increasing on the right, which means that it should be ever closely to its asymptote here on the left. Let's mark that asymptote. All right, so there's that asymptote. So when we do this, we're going to be really close to the asymptote, and we're going to sneak up on it, get a little bit bigger, and then our increase should start to show dramatically. So we're going to increase. We want to make a nice smooth curve here, and it should increase up there. Notice it's more of a sketch, because anywhere in this region we're guessing at what the point would be, and anywhere in this region we're guessing. So it is kind of a sketch, but a lot of times that's all we do with exponentials. We would do an evaluation more than we would pull points from a graph sometimes. We just want to see the general shape. All right, so sketching. Use those 3 points. Your y-intercept, plug in 1 and times ab and 2 and ab squared. If you're graphing, make a table, plot some points, mark your asymptote. All right, well, let's move on then to the other form that we're going to talk about with exponentials, which is vertex form. We're comfortable with vertex form. We've seen it before. We saw it with our absolute value. We said, hey, y equals some value a times the quantity of x minus h, right? Close the absolute value plus k. And we said that inside here, we said that if it was positive, it was awkwardly going to the left, and if it was negative, it was awkwardly going to the right. Again, what I'm referencing is h here. And k, on the other hand, was exactly like we expected. If it was positive, it went up, and if it was negative, it went down. We understand those to be translations of the vertex, right? And the vertex is hk. Well, that works the same way with exponentials. Okay, so let's take a look at how that works. Here's the base form of vertex form in exponential. Right, here's our k, moves us up like we expect with a positive value, down with a negative. Our inside the absolute value here is referenced by being inside the exponent here. And it works the same way. If it's positive, it's going to shift this exponential function to the left. And if it's negative, it's going to shift it to the right. This a value, just like here, it made steeper lines with the v, right? So the larger this was, the steeper the v was. That's also true here. I like to say it happens sooner is another way to kind of describe it, meaning that the curve happens sooner compared to smaller values of a. If a is a decimal, guess what it does? If a is a decimal, it really makes that slow down that curve. So you can either have a slower curve or a sooner curve. If a is larger than 1, it's sooner. If it's a decimal, it's going to be slower. So that's how we kind of reference these translations. Again, all in reference to the vertex form. Now, this is your y-intercept, this is your vertex without the translations, but you'll notice that we have translations here. So there's 2 ways to kind of tackle vertex form. One, you can do our sketching approach, which is we take those points, but we have to mind the translations, meaning that we have to make sure that we address these translations here. Or 2, you can go a little bit more straightforward, and you can go ahead and just graph the points and graph those. But you should be able to, in either fashion, be able to list what translations are taking place. So how did we get these translations? Let's just review that quickly. If we look here, this is on the outside of the exponent, right? So it's outside. So this means that we're going up 3 in this scenario. And this is inside the exponent. It is part of the exponent, so if it's positive, remember we're going to the left, so left 1. And we also want to signify the fact that our b value is greater than 1, meaning that it's a growth. So there's all of our translations. So let's quickly, and I've already done this for us, let's calculate these 3 sketching points because I'm going to show you how to sketch. That's where these 3 points come from. How did I get those? Well, let me show you. What I did was I ignored, remember it's in the base form, a times x to the b, so it has to look like this without this portion of it. A times b to the x. That's what we're looking at to do these sketch points. So what I'm going to do is pretend that these translations aren't there really quickly. And then I'm going to say, oh, my a value for this is 1, right? My growth factor is 2, and I'm raised to the x. So if I plug in 0, 1, that's my a value, right? Because that's where this comes from. A is 1. Then I plug in 1, it's a times b, or 2. And then if I plug in 2, right here, 2, I'm going to get a times b squared. Well, b squared is 4, and times 1 is 4. So that's where those points come from. Again, really quick, no calculations, so that part's nice, right? This, you can see each calculation for each point, so you can pick your path. You like calculations, you don't. But what we have to do now is we have to make sure that we translate those points. So how does that go? Well, now we're going to look at our translations here. And our translation says left 1, which means that that's an xy movement, or we're going to subtract 1 from all of our x coordinates. And then it says up 3, which means that we're going to add 3 to all of our y coordinates. And I'm going to write the translations in here over at the left. So my new translated x coordinate for my first point is going to be negative 1. So I'm subtracting 1 from 0, it's going to go to negative 1. And then I'm going to add 3 to this one, which is going to give me the point 4. I'm going to do that for the next point. This coordinate here is going to go down 1, so it's going to go to 0. This 2 is going to have a 3 added to it, so it's going to go to 5. This point here is going to be subtracted by 1, it's going to go to 1. And then this y coordinate here is going to have 3 added to it, it's going to go to 7. So there's my newly translated points. These are my sketch points. I did the translations, and I came up with my new translated points. So let's go ahead and graph those. So negative 1, right, on the x-axis, up 4. There's my first point right there. Then I'm going to go to 0, 5, and then I'm going to go to 1, 7. There's my 3 points. Now, your translation of your asymptote, right, let's make this a different color so it stands out. My asymptote is going to go up 3. So it's going to shift up 3 from where it would be here. So my asymptote is going to be right along this line here. I want to mark that first so I know where my boundary is. All right, so now that I have that, let's go ahead and draw my line in. I know that I'm going to get, it's a growth, so I should be increasing up to the right side, and I should be getting really close to that asymptote on the left. So I'm going to sneak it up here, and I'm going to have a nice smooth curve. And that's a nice sketched exponential function. Again, you can pause the video, write these down. That's just a quick calculation. If you prefer making a table of values, it's great. You get to use some of your exponent properties. You can see here that we've taken negative exponents, plugged them in, moved the base down. Yeah, you get to practice your properties that way. Here's another one. I'm going to just show up here. You can see again our translations. Let's talk about the translations while I show this to you. This one here is a decay. So that would be worth noting. It's a decimal or a decay there. So that's a decay. It looks like it's moving down 3 as right here, and this is a negative 2, which means it's moving to the right. So we've got a decay down 3 and right, and then there's my points that I pulled out. Here's my translated points over here, and I've marked my asymptote and I sketch it in. Okay. You'll notice though in any of these I didn't reference the fact of none of these a values are negative. If any of these a values are negative, it would flip the function over. I think we did that in the last section. So a quick little review just to kind of say here's all of our translations. H is your left and right movement, correct? If it goes left, it looks positive. If it's right, it looks negative. Okay. K is straightforward. Up is positive. Down is negative. Growth or decay, this is if b is greater than 1, or if it's a decimal, meaning that it's the b value is between 0 and 1, some form of a decimal, that indicates it's a decay. And remember, decays are, that's the negative growth. Decays should be decreasing from left to right, where growths are increasing, either positive or negative in that fashion. Again, from left to right. A value does change it, makes it sooner or later. So if you have a larger A value, it's going to start to curve sooner. If you have a smaller A value, or especially a decimal, it's going to make it curve much later. And then if A happens to be negative, it does flip the graph, and that's where we get our negative growths and our negative decays. All right, so that's a nice little quick summary of this. I'm not going to do the Desmos to keep this short. I might show it in class, but otherwise you should have a nice review on how to graph exponents, and we'll see you using it in class the next day. Have a good one.